first example, we have an ideal nozzle. So basically, you assume that you don't have friction and you don't have any kind of like losses in this problem, and then they say find V2, right? Find V2. So what should I do? We have velocity here, we want to find velocity here. So the solution to this, I can take and streamline. Let's say there is one of this particle here, it moves like this. Streamline. And then I can write all its momentum and continuity equations again from scratch and write it. But an alternative easier way is to just write Bernoulli equation. And since I have the assumption of ideal, I can write the Bernoulli equation, right? So if I do that, I get what? P minus 1/2 of rho u squared plus P plus rho g is equal to delta H is constant. So that's a Bernoulli. So I can across a streamline this constant along the streamline. So I know this is streamline that passes from point 1 and 2. So anything here is velocity 1 or u1. Anything here is velocity u2. Also pressure here, pressure p2, and the density is almost constant. It's incompressible. So this equation is perfectly valid. So let's write it. So you get 1/2, rho is basically same, u1 squared plus p1 plus rho g, this is z, z1 is equal to the same amount as 2, p2 plus rho g, z2. Now, if you pay attention, there may be a difference in height. That's the reason I draw this streamline to show what we deal with this term, Z1 and Z2. If this was really significant, that means this cross section was just so huge, and the other one was just so tiny, that there would be actual height difference between different points. You can never make the assumption of constant velocity, uniform velocity in the real life, because of that z difference, the gravity difference. There is no way to cancel it. But look, in the real life, when you build that in a scale, it's like this. Right here. It's like this. You don't even see that change. It's so a slow change that it's like constant cross-section height. That means the delta z here, in fact, is kind of exaggerated in the y direction. It's very, very small. That's the reason we make uniform flow. In other words, instead of this point, you could take this point here, and because the velocity is same, instead of this streamline, you could take this streamline, just at the center. And this is the second streamline. Streamline number 2. And then you always see that it's actually u1, u2, and this term is 0. They have the same elevation. Right? So that's the reason that term is 0 here. So I get what? I get 1/2 of rho u1 squared, and let's plug in number here. So I have 1/2 rho is 1000 times u1, which is 1.5 squared plus p1. I don't have p1, so I just write p1 is equal to 1/2 of 1000 times u2 square. I don't have u2, that's actually unknown, find u2, plus P2, and I don't have P2. Now, immediately, if I investigate that, I realize that, well, I have just so many unknowns, P1, P2, and then U2. And then what should I do here?
You have delta P, so you can subtract P2.
So basically the key here is you have the delta P. You don't need to have P1 with P2. You could, I mean, finding the absolute pressure at the point these days is not really a hard thing to do. But what you really need here, if I rearrange this equation, you all need is delta P. That's the reason the question uses delta P, right? So I can do this. I can say 1/2 of 1,000 times 1.5 squared minus 1/2. Shift this to right, and then you can bring this here, right? So P1 minus P2 plus P1 minus P2 is equal to 1/2 1,000 U2 squared. So here you have this, if you substitute here, you say delta P. You say
Isn't that negative?
yeah, that's a negative. That's a negative. But let me substitute here numbers. So you have 1/2 of 1,000, 500 times 1.5 squared. So this delta P, put it 1K. I put 5K, wrong number. It's just 1K. So if you put 1K here, what you get? This is negative 1K. So if you put it in a calculator, what do you get? 1/2 of 1,000 times 1.5 squared minus 1,000. You get 125 is equal to 500 U2. And then you solve that with U2. We get square root of this value. So you get U2, solving that with U2 is going to give you U2 is equal to 0.5. Okay, we're checking. If you have, I may say, find the pressure difference that can actually cause this thing to choke. So you're looking for having the same velocity here. How much the delta T will be so that you can't pass the fluid. So this same problem, we can have alternative question type for exactly the same problem. Now, next problem, next numerical problem is this problem. That you have this aircraft you mentioned last time, and this aircraft is flying. There you go. With the velocity. So this aircraft is flying with the unknown. And we want to measure the velocity. So measure the velocity, we put the pipe here. There you go. And here I can measure P, call it P. So I can measure it. And then this aircraft is flying, but look, the free stream or like at infinity, let's say you are inside that aircraft, and then at the infinity, like here, the speed is what? 0. By ignoring the speed of wind. There may be some wind going that way, but the speed of wind compared to the speed of the aircraft is very small, right? So you can almost say the speed here is almost 0, right? What about pressure at infinity? Then the question is, are you talking about at the top of mountain or sea level? Well, usually they say sea level. The pressure at infinity here, call this point 0. Or you can say P infinity. I mean, this different notation, but we're talking about at infinity. The pressure there is what? 100 kPa, 100 kilopascal at the sea level. So this point, call this point 1, and then there is a speed line that goes from infinity all the way to here, and then around it, right? Here, goes all the way here, and stagnates. That means it stops here, and the rest of them, they go around this pipe. One there goes around this pipe. So pay attention to this particular streamline that starts somewhere at infinity, maybe here, and goes and just stagnates here. This particular streamline, very special streamline. It exists that particular streamline that starts somewhere at infinity, but it starts at the tip of that pipe. Right? So across this streamline, write the Bernoulli equation. Can we write the Bernoulli equation?
Yeah. Honestly, why not?
Why? Let's say this aircraft is flying with a very low speed. We can't, right? Because you see, nobody is touching the free streamway. There is no viscosity, there is no dissipation, and the speed is low. So the assumption of incompressible, you see, in this equation, rho is constant in value. If the speed is high, the density may change, compressible flow. So that equation is not valid. Again, there exists a Bernoulli equation, but that's different for compressible flow. It's more complicated, it's longer. The equation there is for incompressible. So if the speed of the aircraft is very low, this equation from the tip of the pipe all the way to infinity is perfectly valid. I can use it. Now, what if this aircraft is flying near the speed of sound? What happens? If you fly near the speed of sound. Yeah, first of all, this density in this equation is not constant. That's the reason we took it out of the surface integral. You remember when we did the line integral for the Bernoulli equation? In the line integral, we took it out and said it's constant, and we did B dot grad B dot dr. And then the integral was just piece of cake. In that case, when the speed of aircraft is high, near the speed of sound, the density will change, and then we have a regime called compressible regime. And that density is different. That means this equation is not valid. That means if I build my cube and sensor, and I put an indicator in there so pilot can see it, the number it shows is not valid when pilot goes with high speed. It shows some number, right? But that is based on this equation. That indicator is calibrated in the cockpit, is calibrated based on this equation. It's not calibrated based on the actual compressible Bernoulli. So that number is not valid, first. Second, when you move with the speed of near the speed of sound, then you get something called shock waves, right? There are shock waves. And if you put this probe here, or here, or here on the wing, because you get a shock wave, you have a delta P across the shock wave. I'm pretty sure you have seen that shock wave. It's like when a military aircraft goes fast, and you see it's like a curtain wrap. It's like a white wrapper around the aircraft. That's a shock wave. So you get a significant delta P pressure drop. So if you put your sensor here, the value it measures is totally rubbish. It's just not valid. So you see, the reason they put this just in top of the aircraft before even the shock, because shock starts from somewhere on the aircraft, it goes like this, like that. That's the way shock starts. It doesn't start here unless you go like very high speed, like hypersonic. That shock moves here. So they put this probe just before the shock forms. So even if you go compressible, you get a number, right? And they have a calibrated form of Bernoulli equation for compressible. So they designed this calibration between the pressure measured here and that, such that it also works in the compressible, even if the density changes. That's a different equation. So they designed it based on that. But if you know this, you can do that too. It's not a big deal. If you can do this, you can do that too. It's just you solve for different type of equation. But the principle is the same. Now, with that said, let's take this number. So you have P0, rho 0, and the density of air, take it 1.3 kilogram per meter cube at sea level. And then we want to find a relation for velocity of aircraft. And let's say I have P here. Okay, P here is given. Call it P. How can I measure P here in the stagnation point? Well, put a pressure sensor inside the cockpit. You see, there is no flow going here. Why? Why there is no flow going here? Why? Because it's stagnant. You see, the flow, in that tip, the air is pushing it in, but it's not moving. It's just stagnating here. There is no way it can go, right? There is no outlet. So this gets very hard pressurized, and then you can measure the pressure. There is at least 20 ways to measure that pressure, right? So you have this P, and we want to find the velocity of aircraft. Now, write the Bernoulli equation, P1, 1/2 of rho V1 squared plus P1 plus rho G V1 is equal to 1/2 rho V2 squared plus V2 plus rho G V2. Now, you can immediately say that if the aircraft is flying at a very, very high altitude, the height difference may be significant, so you have to include that there. But look, you can say that the pressure at the sea level is not exactly at sea level. You can go a little bit higher than sea level. So you can make this streamline pretty much like flat. So this is a point not exactly at sea level, a little bit higher. So what does it mean? That means you can get to the delta Z. You can always find a streamline that the delta Z is small. But if the aircraft is trying to escape the atmosphere, that term is significant then. So that is small. What else do I have? You have for P1, what is that? So you have 1/2 rho at infinity, 1.3 times V at infinity. What's the V at infinity? 0. Square plus P at infinity. 100 A, right? And this term they cancel out is equal to what? 1/2 rho. What's the V here at this point?
That's what we're trying to V of the plane.
Yeah, V of the plane. Why? Because look, you are assuming, you see, when we wrote the equation law of Newton, sound force is equal to ma. Everything we drive here, everything we started studying in this course and the previous course is based on the Newton laws. the reference coordinate for Newton laws. We call it the inertial coordinate system. You remember that? The inertial coordinate system was a coordinate system that is either fixed or moving with constant velocity, not accelerating, not rotating. In that coordinate system, this equation is valid. So in fact, you can put your coordinate system attached to the aircraft. If you put your coordinate system attached to the aircraft, what do you see for velocity at yourself? At your point, 0. What do you see the velocity at infinity?
The speed of the plane.
The speed of the plane. And vice versa. If you put the velocity on the free stream, right? If you put the coordinate system in the free stream, what's the velocity at this point? V of the aircraft. What's the velocity at free stream?
0.
0. The equation is still valid because we assume that at that particular position, the aircraft moving with constant velocity is not accelerating. If it is accelerating, the equations of Newton's law in the coordinate system attached to the aircraft is not valid. You have to include inertia here. Right? So, here, 1/2 of rho v squared, v2 squared plus p2. Right? And this is p2 is what? We have a P. The pressure in concrete. So therefore, you can solve for V. So you get what? You get, well, multiply both sides by 2. You get rid of this 2. Then this becomes 200 kilopascal. Get rid of that. You get 2P. And then you solve for that. You get 200 kPa minus 2P divided by rho under the square root. Is going to be V2. So that, let's say the sensor here, it measures the pressure is like 51 kPa at a particular time. So put 51 kPa, 2 times 51, it's like 102 kilopascal, minus 200 kilopascal, 98 kilopascal, divided by rho. And because we said incompressible, with the assumption of incompressible, the density is constant all over the streamline. Right, so you can use the density here. 1.3. So you put it there, you get V2. Yes.
Would that equation, final equation, be only valid for 100 kilopascals of your altitude?
Yeah, well, that's the reason they usually announce the wind speed. You see, we say wind speed is 0. If the wind speed is significant, when the aircraft is landing, you have to correct it. And they also announce the pressure at sea level, the density, like if this is different on the top of the mountain. Well, we assume this is like that's like an imaginary concept that we assume that go all the way to infinity, actual infinity, at some point in the sea level that the pressure is there. So with respect to that, there must be a streamline coming to the aircraft that this relation holds. So you can find the velocity there. Now, you may say another numerical problem, because today we just try to solve numerical problems. We don't have any derivation.
So what is that pressure, the second pressure?
This pressure,
Like, how do you exactly measure that?
how do you, that's the next question. That's the next question. How do we measure this pressure? So this is the next question. kg over meter cube. We call this point 1, it's a station, we call this 2. Formation, V1, let's say that I give you the diameter this time. R1, 20 centimeter, R2, 5 centimeter, and velocity here, V1 is 5 meter per second, right? And the density is just water. And constant again, compressible, no high speed. Now, question is, find this pressure height. What's that delta H? I may use a different color here. What's this delta H? And what is this thing? Let me talk about this setup. Well, if you imagine this, we call it schematic. That means just a conceptual drawing to show how it works. But in the real life, if we make a hole here in this pipe and attach this system to that, this flow obviously goes right inside that. It mixes circulation, you mix it up and mess it up. So this is just to show that here, because the drawing is very complicated. If you draw in 3D, it takes some time. If you consider the three-dimensional, well, there is a hole here that is connected to a tube, and another one here on top of it that is connected to a tube. And these two holes go through a piping system, and this is your tube. This is your actual tube. And if you have done lab, done state lab last week, you know that there was a long tube, it goes on top of it doesn't go from what bottom, because it leaks. And then it connected to two columns, and you could measure the pressure in height. Now the question is, so this point is not on the bottom of this, because it's going to be somewhere on the top that there is no way that the fluid is unidirectional, there is a valve, that there is no way that this can go to that, right? So, let's say I have velocity here, right? So here this 5 meters per second passes through that, and then if I have a converging nozzle, what happens to velocity? The velocity will increase. So the velocity, whatever you get here, must be greater than 5 meters per second. So if the velocity increases, what happens to pressure?
Decrease.
Why? Can you tell me why? The Bernoulli, right? Yeah, you can say that, but we're talking about pressure, not velocities. The pressure does not hold the relation with continuity. You're talking about continuity equation. If the cross-section area decreases, the pressure, the velocity increases. But I'm talking about pressure, the delta P, the difference in pressure. What happens to pressure? So if you take a streamline going from here to here, this is a streamline, right? If you take that as a streamline, I know that this is incompressible, the density is constant, friction is very small, right? So I can perfectly between 1 and 2, let's say 0.1, 0.2. I can write Bernoulli equation, and in Bernoulli equation I have P plus 1/2 of rho U squared plus rho GZ is equal to constant. You remember last time we said constant along the streamline. Streamline. Right? So we had that. So look, if this guy is constant, so this sum is constant, and also you see it's level, it's flat. So this term is also 0. It's constant, that means if you take this 2 point, they're the same value, you can just simply ignore it. So look at it. If the sum of these two numbers is constant, when you decrease the velocity, what happens to pressure? increase because the sum is constant. And if you decrease the pressure, what happens to velocity? Increase. There is no way that both of them increase. So you can memorize it like that. In compressible implicit flow, there is no way that both pressure and velocity increase. So here, look, if I make it converging, you know from the physics, the velocity will increase. But the moment the velocity increase here, the pressure is decreased, right? So in fact, this delta H, it should be this way. I get my drawing wrong today. So this goes I here. There you go. Yeah, go ahead.
That's what I was gonna ask about.
Yeah. So you can see because the pressure is higher here, the pressure is smaller here. Why? Velocity is higher. This pushes it more down than here. That means there is a delta H in this column. Now take this fluid, they usually use mercury for this fluid, but because it may be dangerous, let's take just this water, right? The water, and this is the height of the water, height, and I want to compute it. That means if I go to lab and I build this nozzle and I put the fluid velocity here and density, and I measure velocity here, or I use continuity to find velocity here, then what is my delta H? Now this is the problem. Solution to this problem, we use continuity first. So between this point, we have rho 1, u1, a1 is equal to rho 2, u2, a2. And you know that I start from control volume, I simplify all those integrals and I end up with that. But I don't repeat those procedures, I just write this equation right here. But in fact, the correct way to start with 5 steps, instead my system is this, then you write your equation, make your FED, write your equation, simplify, and then you get this equation. Now these two cancel out, so you get U2 is equal to A1, A2, U1. So there's one equation. The second equation is Bernoulli, which is momentum basically. If you simplify, you get that. You get P1 plus 1/2 rho U1 squared. I don't write rho GZ because I said they cancel out at level. P2 plus 1/2 rho U2 squared. So these are the equations I have. Now solve. Put the numbers here. So you have A1 over A2. I cancel out. You get R1 over R2 squared U1, and then this is going to give you 20 over 5 square times U1, 5 meters per second. Now you immediately say, well, you need to first convert it to meter and then put it in the equation, which is perfectly good practice. Every time you see an equation like that, first convert it to this SI unit and then plug the number in. But look at here. These are the ratio of radius. So it doesn't matter if you put inches or centimeter or foot, right? They will cancel out. So make sure they're just consistent. If they're consistent, they cancel. That's the reason I put 20 and 5. I didn't put 0.2 and 0.05. That's an important thing to know. So if you put that in calculator, 125, but look, always put in calculator. Even if you know the answer, please put in calculator. 20 divided by 5 squared times 5. 80. Meter per second. Alright? So this is the velocity at 2. Now that means here the velocity V2 is equal to 80 meter per second. Now let's work on the Bernoulli equation right now. To say 1/2 of P1. Do I have P1? Do I have pressure here? Back to the question that Edwinas asked. Do I have, he asked, how come we have a pressure here at this aircraft, and, you know, I said, put a pressure sensor here, and it was a magic sensor that measured pressure. But it's not really magic. You can use a YouTube and measure it, and that's what I'm trying to get right now. So do I have pressure here? No. I don't have pressure here, so just put P1 plus 1/2 rho 1000 times U1 5 squared is equal to. Do I have P2?
No.
No. Just put it here. It may be a little bit disappointing that you don't have it, but please go ahead and finish it before making any conclusion. Because if you make conclusion too early, you're gonna give up. So P2 plus 1/2 of 1000 times U2 is square. And now I have my U2, and I'll put here 80 squared. So even though I don't have P1 and P2, just like the last example, I can find P2 minus P1, right? So what is my P2 minus P1? P2 minus P1 is equal to, so you say, or P1 minus P2, put it here, P1 minus P2 is equal to 500 times 80 squared minus 500 times 5 squared is equal. Put a calculator. So you have delta P is equal to 3.19 megapascal. That's a lot of pressure here. So you have, if you do all the calculation correctly, you get 500, you can factor out these two, times 80 squared minus, yeah, you get 3.19 megapascal. So the difference in the pressure between here and here is what? P1 minus P2 is equal to a positive number. That means we have more pressure here. And it's equal to 3.90 megapascal. It's like 30 atmosphere. It's a huge value. Why? Because this velocity, 5 meters per second, for this cross section is hard. And it's water, it's not air. If it was air, it would not generate this much density. In other words, this would be 1 instead of 1,000. So you divide that with a factor of 1,000, so you get something about atmosphere gauge, right? So now, my question is find this delta H. So how can you find that? Now go back to another system. Now take this as your system. All right? Take this point, this was 1, 2, make this 3, and then make this point 4. And this is pretty much FPD. And now, equations. Before even I write equation, does it move? Does this fluid move? The black one? You said yes. Why?
As the fluid moves,
Yeah.
it's going from one side upwards to another.
No. Does it move? I already explained, you remember, I drew a three-dimensional here, I erase it. And I say we bring this pipe, we put it on top, so there is the fluid is not circulating here, it's not moving. The connection here is between them are air. So you only have pressure touch, there is no movement. Now, this fluid here, does it move?
No.
It doesn't move, right? So what relation do I have between point 3 and 4? It doesn't move. Hydrostatics, it doesn't move.
So could you do rho GH?
That's right. The previous chapter. That's the reason the book put this chapter in a sequence. Like first you do hydrostatics and then we do dynamics. Because this is just simple. It's not even moving. So that means what? the delta P here, P4, look at this column. P4 minus P3. Right here, P4 minus P3. Put it like this, P3 minus P4 is equal to rho GH. Rho G, what H? Delta H. So that means delta H is equal to the delta P, which in that case is 3.19 megapascal, divided by rho 1000 times 981 G. Now you see that the advantage of fluid that are very heavy and dense is you increase this is the density of this fluid. If you we use water, which is not a good choice. It just moves a lot. If you use a heavy fluid here, this density will increase, so the delta H will be smaller. So in the lab, I do not need to make a column of like 12 meters. Just to measure like in the aircraft, if you put a column of 12 meters, it's not even practical. Give you a very wrong number. So that's the reason they use a heavy fluid with a high density, because it divides by density of the measuring fluid, the hydrostatic problem. And then you get delta H. Now, next question, if I say, now this problem right here, I give you the discharge coefficient of discharge. So let's first define the coefficient of discharge. Let's say the nozzle is not perfectly made. And there is a coefficient of discharge of 0.821, i.e. coefficient of discharge is equal to 0.821. Then find the actual flow rate. Flow rate or mass flow rate, or MDOT action. So that's the next question we give in the next meter. You have this configuration, but this is not made of like it's a perfectly made symmetric material with zero surface roughness and all those things assumptions made. So what happens in the real thing, as I mentioned before, you get a small vortices here, and the actual cross section that the flow can pass through it is smaller than this that I show here, because of those vortices here. So you get something like choked a little bit. So the flow rate, if I have a flow rate here, what's the flow rate here? The flow rate here is rho 1000 times the area of this times 5, right? And this always same. It doesn't matter this cross section. The flow rate is same because nothing is accumulating. Equation of continuity, right? The flow is incompressible. It's not compressible, and it's time independent. But look, if this is not made perfectly, you get some vortices here, so the actual cross-section that the flow sees is going to be smaller than the ideal case. And solving that, again, you can solve from Newton laws, but you have to include also the momentum viscous term in the momentum equation. And if you have a very good mathematician or supercomputer, you can solve that without even considering the coefficient of discharge. And then you can start get the pattern of flow, where the flow goes, and what area it sees, and you can get completely the actual flow rate without any problem. But that is very time consuming. It requires you to have a computer to model this, to run it. Usually it takes 2 days for computer to give you an answer. So imagine if you want to design this. Every parameter you change, you have to wait another 2 days for computer to give you an answer. That's not really practical for engineering. That's the reason we use coefficient of discharge. So this coefficient of discharge is given to you for this type of nozzle, and what he has to find the actual flow rate. Now, solution to that, I write the equation here. So you have coefficient of discharge is m dot actual, m dot ideal. That's what you have, right? So what do we have for m dot ideal? M dot actual is what we're trying to get. Is what we're trying to get divided by m dot ideal. What you can write for m dot ideal? Let's say at this cross section is
Rho UA.
rho V1 A1. So you pretty much have everything ready. And substitute number here, you get 0.821 is equal to m dot actual divided by rho, which is 1000 times V1 5 and times A1 5. Let me do something here, and then I ask you what's wrong here. Something is wrong here. Can you tell me?
Do you need to convert the 20 centimeters to meters?
Who's there? How many quizzes you got so far?
That'll be my third one.
You're terrible. Guys, please contribute to the class. You know, I know you may say, well, you get 100 or 95 in all your tests and quizzes and you pass with 8, but that's right. In fact, it's not happen. But it's easier to contribute. Because if you contribute, if you say something, and if it's correct, I can give you a quiz. So here, you may say, well, last time you did not convert it to meter. You know, we have, some of you are, I see you're smiling, laughing at me. Yeah, it is stupid, guys. Yes, this is very low level discussion, high school discussion. But we have, when I grade the test, we have people doing these mistakes. And I'm pretty sure there are some people right now say, he didn't convert it to meter, but here he says it's wrong. I have to convert to meter. I'm confused. Well, look, this is we divide two things together. Doesn't matter if it's inch, or feet, or centimeter, or kilogram. You divide, they cancel out the unit. But here we do not divide it. Alright, so next midterm, please don't do mistakes like that. 0.2. So m dot actual over rho v pi r squared is equal to that. So what's your m dot actual? Solve that for m dot actual, you get 0.81 times a value times I. Correct. So m dot actual is 500. Is equal to 5.8 kilogram per second. Look at it. That's a huge mass flow rate. It's half of a metric ton per second. That means in 1 second, like this, you have a half of metric ton. How much is half of metric ton? Like 8 times my weight. They pass through this 20 centimeter radius, which is this part of this thing. Why? Because the velocity is 5 meters per second. That's a huge velocity. That's like you're running. more than running, like running fast speed. So that's the reason the height in the previous problem, if you plug in number, the height difference in that tube is so huge. That's the reason they put a heavier fluid, like mercury, and even heavier than that. Right?
That's like the same forest. Oh, why?